I'll wait for a minute or two before starting. Specifically, I think overall in the talk, I want to highlight what this is referring to, I guess. But we'll start with this part. In fact, most of our talk would be about this part. But I guess if there's some, I guess in between, I may talk about things like complexity or whatever that means, right? Um, exactly what this area is in general. It's basically an area that has come from um, well, I mean, of course, that's this part, and again, there's mathematics certainly, but recently there's also been a lot of computer science involved with this. So it's like often huge sub areas of this are also called computational economics. Mm. It's a really interesting area where we basically take uh, economic things and like something that's inspired from a real economic setting, and then we sort of abstract it and make it really mathematical. Sometimes it's mathematical enough to be far off from reality, but well, that's what maths is. Nobody cares about application. Okay. Okay, so let me get started. So okay, so let's talk about a very standard problem. It's called prisoner's dilemma. Okay. So the idea here is this: there are two prisoners who are on trial for a crime, and they've been separated into rooms, and each of them can individually confess to the crime or remain silent. So what happens is, if say the two prisoners are A and B, and if A confess, so if both of them do not confess, so let me make a table. So there's A and then there's B. So you have the choice of confessing or the choice of not confessing, that is being silent. Confess or remain silent. If they both remain silent, then they each get, I don't know, 1 year in jail. Right? But let's say if A is silent but B confesses, then, well, actually, let me just make this 3, just full. But if B confesses and A doesn't confess, then B only gets 1 year in jail while A gets 10 years in jail. And if A confesses while B remains silent, then B gets 10 years in jail, and A gets only a year in jail. And if both of them confess, they both get 5 years in jail, right? And let's just say A and B are not particularly friends; they just happen to collaborate on the crime. And yeah, so what should A and B do? Ideas?
Something to do with probability.
What sort of a probability are we talking about?
Like if you confess, you can either get 1 or 5 years of jail. and then
But it's not so much about probability as it
oh,
is about trying to think of what the other person's doing. It's not like the other person is choosing at random, right? So uh they're both selfish, let's say. So
I see.
yeah, I guess in some sense you're everyone who said that they both confess is right, because the idea is that no matter what you do, it's always better to confess. For example, suppose A remains silent. Say A is silent. Uh, So let's say B confessed and A remained silent. Note that then it would have been better for A to have confessed, because that reduces jail time from 10 to 5. And even if B were silent, it's still better for A to change silence to confession, right? So either way you decrease, like, if no matter what, okay, so I should write it as this: no matter what B does, let's just fix this. It is better for A to confess, for A to confess. Strictly better, in fact. And that's the same is true for B, right? No matter what A does, it's better for B to confess. And so, yeah, but the point is that they don't have the time to discuss. So, also, even if they're able to discuss, what prevents one of them from confessing anyway, right? uh, I mean, then they're not trying to minimize the total time, right? They're trying to minimize their own time. So yeah, the point is that since you don't have information, the whole point is that it doesn't really matter what the other person is doing. The point is that no matter what the other person does, it's always better for you to confess, right? Because it reduces your jail time. So, but that seems a little weird because both remaining silent would have been better than both confessing. And so that happens actually. So indeed, if these agents are selfishly interested, then they should both confess, which makes sense, right? Because if you don't know about what the other person is doing, then confessing is always strictly better. Like, if you remain silent, you won't change what the other person would do, and so might as well just confess, right? But of course, the whole thing changes if there's some third person who can decide for the both of them simultaneously, but that's not what's happening here. It's just these agents individually, and they don't know what the other person's doing. Yeah. Okay, this was one example. So I just want to go through a few examples like these. So let's go through one more example. So um, let's go through. Okay. Yeah. Let's look at this. Um, okay. Okay. So I'll describe this in this particular form. So there are n players.
The screen is no more being shared.
Oh, that's weird. I wonder why. Do you see it now?
Yes.
Okay. So there are n players, and uh, there's some. Okay, so each player wants to send some information across some channel. Say, say, think about it as like a literal wire, right? And then we want to share some resource along this. So, okay, so um, okay, so let's um, okay, so let's say we have this channel, right? And there are n players, and they want to send information through this channel to some source, some, I mean, destination. That is. So these players are the sources. And this information for, so okay, so each of these players can send some, let's say this player one sends x1 units of information along the channel, and this sends x2 units of information per minute or whatever, right? So it's some unit of data divided by time, like size divided by time or something, right? So then this is xn, and and the maximum capacity of information on this channel can be 1 unit. Info. This is a capacity of this channel, right? And so each of these xi can be at most 1, and we also need x1 plus x2 plus up to xn to be at most 1, right? But now these players don't know what the other players are doing, right? So um, but the problem is that uh, the quality of this channel deteriorates with the, okay, so maybe I should uh, define it a bit more rigorously.
So the people are sending the information like one at a time or like simultaneously, like
They will
this
send it
together.
simultaneously. Yeah, they send it simultaneously. Yes. So okay. So here's the tragedy. The point is that if somehow, okay, I should mention it separately. Okay. So just to make it a bit more concrete, if it happens to be the case that x1 plus x2 plus so on up to xn is more than 1, then no player can send info, because I don't know, something happens to the channel. It just doesn't work. Yeah. So any information. Yeah. But if x1 plus x2 plus up to xn is not more than 1, which is it is less than equal to 1, then the okay, the value that player I gets is xi times the total amount of bandwidth left, that is summation j equal to 1 to n of xj. What this means is that basically there is some sort of a deterioration of the rate in which rate of information flow as the load on this bandwidth increases. So that is, so so let's say if x1 is 1 by 3 and x2 is 1 by 3, then and all other xi's are 0, then so let's say this is 1/3, this is 1/3, and everything else is 0, then the value attained by this player 1 is 1/3 times 1/3, and by x2 is 1/3 times 1/3. Yeah, because there's 1/3, and then the amount, the the capacity that the bandwidth can hold is further hold is 1 by 3, and so that's proportional to the the of the speed of the information, right? So and so we have such a trade-off, right? Okay.
Oh wait, is this like
This-
1 by 9 is the next amount of information which can be transferred?
no. 1 by 3 into 1 by 3 is sort of like the the happiness of player I, if that makes
Ah,
sense,
okay, got it.
right? So this is like so 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 player I is able to send xi units of information, but but that it comes at a cost that since the since the channel has been since the channel is carrying so much data, its speed reduces as the amount of information it needs to carry increases, and so
Oh,
there is
wait,
like a
why is the next amount of information carried by the player not 1 by 9?
uh, I what would that mean exactly? So um, because this is like a rate of information, like this is not x1 units of information, it's more like x1 units of information per second or something, and then we can only carry at most 1 unit of information per second or something. So just think about it. So forget the whole setting, just think about it as this: you have n players and each of them has to choose a number from 1 to n, so from between 0 and 1 reals, right? And if the sum of these reals is more than 1, then nobody gets anything, and if the sum is less than equal to 1, then player I wins this amount, right? So this is like a winning of the player, right? So maybe that setting is easier to see, right? So
Oh, okay, yeah.
yeah, so no player wins any money. I think I should write it that way. So the value that is more like the money that player I gets is this much, right? Okay, and we know that each xi will be chosen between 0 and 1. I mean, there's no point choosing anything more than 1, right? Because then you don't get anything. And so, what should a natural strategy look like?
Choose a number which is like just less than 1 by n.
Oh, by the way, we know n, so we know n. Less than equal to is fine, by the way. So, uh,
But like if everyone sends 1 by n, then the amount which a person X gets is zero always. No?
that is true. Yes. Good.
Yeah,
Good to
everyone
know.
should pick 1 by n. Then you'll get 1 by n in the end.
Uh, no, but the amount that then the player I gets is 0, right? Because this term becomes 0. If each xi is 1 by n,
Oh,
this becomes 0. Yeah. So that's a problem. So not only do you, yeah, it's weird, right? So yeah. So okay. So yeah. So
I
how would
think
we think about
so.
this?
Like we can generalize it as like the prisoner's dilemma, and everyone should send one only.
But then nobody gets anything. Isn't it just
Okay, like
strictly
zero
better
point
to?
nine nine nine.
Even then, nobody gets anything.
Yeah, but if we can rule out this similarly, like as we ruled out in prisoner's dilemma.
Uh, but but why is it strictly better to choose 0.999 over anything else? Here it was clear, right, that no matter what the other player does, it's strictly better to confess. But here it's not clear why it is strictly better to choose 0.999 over
No, if you
any
pick
strategy.
0.999, then 1 minus the summation thing will be negative.
Yeah, exactly, that is true, but the point is that okay, so suppose we somehow suppose player 1 somehow knew the values of x2, x3 up to xn, then what should x1 be? Can you figure that out?
1 minus
Yeah.
1 minus that by 2.
Yes, exactly. So why that is true is because, so let's say the sum of the others, that's the only thing we care about really, right? Is s. If s is at least 1, then obviously there's no point doing anything. So just pick whatever. But let's say s is less than 1. Yeah. Then what do we need to do? We have x1 times 1 minus s minus x1. And we want to choose an x1 that maximizes this. And so what is the x1 that maximizes this? 1 minus s by 2, right? This is the best x1 for a given x2 up to xn. Unfortunately, this depends on s, right? Unlike here in the prisoner's dilemma, well, here we had binary variables. Here we have like a range of variables. But in even here, so if B confesses, A's best strategy is to confess, and if B is silent, then A's best strategy is to be silent, is to confess. And so this remains the same throughout. And so A can just simply confess, knowing that it's like the best possibility given that B's choice is fixed, right? But that's not true here. Okay, so there's some fundamental difference between these two problems. So let me just highlight that there is no single strategy that always does better than other strategies, right? Okay, so great. So fine. But now let me propose to you a way in which they could have discussed something before. Yeah, let's. So, okay, so let me. Okay, so let listen to this example. So we have x1 equal to x2 equal to so on up to xn equal to 1 over n plus 1. So now suppose, okay, so they discuss this strategy somehow. So let's say somehow they were able to discuss and come up with this strategy, right? Now consider a single I. Is it beneficial for this player I to change their value to something else? Suppose just I wants, suppose player I just wants to change their value and cheat, right? So is it beneficial for them to do that, assuming all other values are indeed 1 over n plus 1? That is, if xj is 1 over n plus 1 for all j not equal to I, is it beneficial for player I to change their strategy?
No,
Why?
because 1 minus s by 2 is 1 by n
Exactly.
plus 1.
Exactly. The answer is no. And we can figure that out simply because the sum of the other variables is so the benefit would be xi times 1 minus n minus 1 over n plus 1 plus xi, which is equal to xi 2 upon n plus 1 minus xi, and this is maximized at 1 over n plus 1. And so we have this sort of a strategy which is in some sense stable, right? So there is some sense of a stability here. It is stable. Let me just put it in quotes. Stable
Does
in some
every
sense.
person only want to increase its price, or do they want to
Yes,
increase
yes,
its?
every agent is selfish. Yes.
Okay.
Yeah. Yeah. So these players are all playing for themselves, right? So uh yeah, so we're looking at yeah, so all these players are selfish. So we're all just concerned for ourselves. Right? The comment says hence all should go for 1 unit of info, but 1 unit of info gives you zero value, right? So it's like strictly it's at least as good to go for 0.1 than 1 because 1 definitely gives you nothing, right? So okay. Fine. So we have this sort of a stability, right? And so what is the sum of values obtained from this strategy?
N by n plus 1, or
No, actually, you
oh,
forgot this other factor, right? Okay, what is the value obtained to player 1 or any player rather? It's just 1 over n plus 1 times 1 minus sum of n plus 1, right? So this is the value obtained for each player. And so I'll multiply this with n, right? So this is n over n plus 1 whole squared. Yeah. But why is this so sad? Like this, it just feels like, it just feels that as if there are n agents trying to send info, then we have this sort of a strategy which is somewhat like an equilibrium, but the overall value that they get is so poor. It's like less than 1 over n. And so the value is kind of decreasing as n increases, which is really sad because you can sort of simulate everything with n players than with smaller players. And so it's as if competition is benefiting nobody in some sense, right? So I mean, think about the strategy that someone recommended in the chat. I think is to use this strategy 1 over 2n. And in fact, for any given x1 x2 up to xn, which is such that their sum is less than 1, note that the sum of all values, so let me call vi as xi times 1 minus s, where s is the total sum, then note that v1 plus up to vn is s times 1 minus s, which means that if s is half, then we can actually achieve a social happiness of 1 by 4, right? As opposed to 1 by n. Right? And so this is really bad, right? Because in usually in these practical situations, um, usually in these practical situations, n is really large, and so if people are sort of greedy, then nobody benefits. And even if we have such strategies which are sort of stable, then we get such a poor 1 by n thing. But when we go for strategies such as choosing x1 equal to x2 equal to up to xn equal to 1 over 2n, which achieves this value of half 1 by 4 overall, the problem is that some xi may benefit from increase. Each xi in fact benefits from increasing their value. And so this xi itself increases their value, but that decreases the values of others, right? So that is more. For example, if n is 3, then x1 equal to x2 equal to x3 equal to 1 by 6 would fetch each of them a value of 1 by 12 each, right? Because 1 6 times the sum, which is 1 by 2, which is 1/12. But now what happens if x2 and x3 remain 1 by 6 and x1 becomes 1 by 3? Yes, 1 by 3. So what happens now is that now the total sum is um, 2 by 3, and so the value for x1 is 1 by 9, which is more than 1 by 12, but the values of x2 and x3 have become 1 by 18 each. And so there is a selfish motivation for player 1 to increase its value, increase increase its xi, right? And so the problem is that solutions that achieve the maximum total value are not solution are okay. The solution here that achieves max total value is not good in the sense that each player can increase its own value and sort of cheat, while strategies where no player individually can change its value and increase its value by changing its xi are solutions where the total value is very poor. And so there is some sort of a trade-off like this, right? We'll talk more about this, but I just want to give one more example before we define terms. Okay. Uh, okay, so let's look at this. Um, let's just look at rock, paper, scissors, right? Okay, so we have two players, A and B. And so we have rock, paper, scissors. Sorry, let me just write it a little wider. Yeah. Okay, can you help me out with the grid here? So it's 0, 0, 1, -1, or maybe let's just keep it 1, 0. I don't think it should matter. And then this is 1, 0, 0, 0. Right. Um, sh- does this make sense?
Yeah.
Okay, great. And so now what should the strategy be? Or maybe let me just modify this and actually put -1s. So let's just do that. Okay. And so now what should the strategies of A and B be? Is there any strategy you see where there's no benefit for someone to change or something like that? Just how here
No,
we had this.
but I don't think there can be any strategy, because like for everything you pick, like there's one thing that you can defeat and one thing that can defeat you.
Good. Yes. So it's not like A has some A can choose something from our rock paper scissors and B can choose something from rock paper scissors. such that, so that is, we can't choose a symbol from here and a symbol from here such that a comma b is stable, because that's just not true, right? Because if a and b are the same, then say both are rock, then a will benefit by choosing paper, right? So if somehow if we knew that b is rock, then a might as well be paper, but then if b is paper, then a might be scissors, etc., right? So there's nothing of this sort which is stable, just how we had it before, right?
What do they mean by A comma B is stable?
Okay, so what I mean is that uh what I mean by this is that there, okay, so uh I should define stable here. I'll define it more concretely again. By stable, I mean uh for okay uh changing, okay wait, so uh keeping b fixed, there is no benefit from changing a, and vice versa, and this the same thing, keeping a fixed, there's no benefit from changing b. That is, in some sense, a is one of the best responses to b, and b is one of the best responses to a, and that was true here, right? Choosing xi equal to 1 over n plus 1 was the best response if all others are 1 over n plus 1. And similarly here, choosing confess is the best response if the other person you confesses. In fact, here we have something stronger. Here, confess is the best response no matter what. But for here, for example, so we have this tuple 1 over n plus 1, so on up to 1 over n plus 1 is stable in the sense that for any player I, if all other players follow this strategy, then there is no benefit obtained to player I by changing their strategy. And so I'm saying that there is no such a comma b which is stable here, right? In fact, you can just brute force and show that, right? So for example, if a b is r comma r, it's certainly not true, right? Because I can simply benefit by changing this, right? Or if it's s comma p, then then um, then b can benefit by changing this to sr, for example, and all other cases are symmetric or whatever, right? And so we don't have such a stable uh, strategy, right? Okay, is this clear so far? In all three examples, are there questions?
What was the purpose of making it 1/2n?
Oh, so here I just took 1 over 2n to maximize the total value. So I just wanted to find a strategy that maximizes the total value obtained, which is this quantity, which is maximized at s equal to half. And so 1 over 2n each is one example. Of course, there's other examples such as x1 is half, and then all other x2 is 0, for example. That's also an example that maximizes the total value. But I also wanted to point out that this is, even if this maximizes the total value obtained, it doesn't maximize it. It incentivizes the players to lie and change their values. Does that make sense?
Right.
Okay, great. Of course, this 1 over n plus 1 each is also prone to many problems such as two players collaborating with each other, etc. But let's just say that let's just keep this concept of stability and let's just define that first, and then maybe if there is time, then we can talk about uh, those things. Yeah. Okay. So let's talk about the first game again. So okay, before that, let's formulate what a game is in some sense, right? So okay, so we have n players, and player I has a set of strategies. So has a set of strategies Si. Okay. And to play the game, each player actually chooses some strategy from this set, right? So then each player, so for example, here the set of strategies is to play R or P or S or uh, among other strategies that we'll talk about. And so each player picks a strategy, yeah, and then we have this set S. I mean this tuple S, which is a set of strategies. Yeah, so it's like a vector of strategies, which is a subset of this, of course. Yeah. Okay, great. And so given this vector of strategies, we have some sort of an outcome, right? And so often we'll have uh, um, so we have this outcome which is like a payoff to a player, right? So and then so that is we have a function ui from the set of strategies, which is, let me call this capital S. And so this is a function from capital S to some number, let's say reals for here. It could be something more complex, but let's just say reals. Yeah. For example, here, so for example, in this second example, we had a UI of the S's were actually X's here was equal to xi times 1 minus summation xj, right? So this was like a payoff. It's called U because it's called utility function. It's a utility obtained to player I. That is, it's like the profit or the value or sort of like a happiness that player I has after this whole game, right? Okay, great. And so let's talk about. So let's revisit the first game, which is Prisoner's Dilemma. So note that we had this strategy for Prisoner's Dilemma, which is S1 equal to confess such that for all S2, the utility obtained to, okay, so to player 1 through this is at least as much as the utility obtained if we change our S1 to something else. Does this make sense? Just let me know.
In this case, S1 dash should be silent, like there are two options.
Yes, yeah, there's just two options here, right? I just want to make sure if this makes sense. But now note that we could also have concepts which are in some sense randomized. For example, I could have, actually let me talk about that later. Uh, but I hope this makes sense, right? And so
Wait, what's
in
the S1 dash thing?
it's any other strategy in capital S1. So we have this.
Okay.
Yeah. So basically, this is a strategy such that no matter what anyone else does, it's always best to pick this. Yeah. So so it's what is called a dominant strategy. So we say that SI is a dominant strategy if for for player I, because I've just indexed it as I, just for all S1, S2 up to so let me call this SI star. Yeah. For all S1, S2 up to Sn in S, this tuple, right? The utility obtained by this strategy is no more than the utility obtained if I replace Si with this Si star, right? Si minus 1, Si star, so on up to Sn. That is, no matter what Si is, it's always at least as good to pick Si star as the strategy. Yeah. Yes, S is S1 cross S2. Yes, cross Sn. Yeah. Okay, so I hope this is clear. But
So in the previous example, SI star was SI and SI was SI dash.
yes, so I'll change that. Yeah, this is this okay.
Yes.
What is xi in the definition of utility function?
What is SIN?
What is xi in the definition of utility function?
Oh, so I was actually referring to the other thing, to the second example in the tragedy of the commons thing. But it's just something from it. It's just some utility function, right? I mean, here the xi's were exactly the si's. So if you remember this problem, the second problem, each player picked an xi, right? And so the strategy itself was the xi. Is that clear?
Yes.
Yeah. Okay. Great. Okay. So now we could have something called a dominant strategy equilibrium, which is that every player has a dominant strategy. Strategy equilibrium. This is like the best kind. So this is the best kind of equilibrium we can hope for. So this is, well, sorry. This is awesome. So what this says is that S1 star up to Sn star is a dominant strategy equilibrium, also just called DSE, if for each player I and any other strategy S prime, we have that the utility obtained to player I in this. Okay, um so often we, okay, so So we have S prime I as what the player I is doing, but s- so we'd also refer to S minus I prime to what everyone else is doing. So I hope the notation is clear. I'm sort of overloading notation. That is basically, so let me write this out first. So S1 prime, S2 prime up to Sn prime, and there's some Si prime in between, is at most as much as the utility obtained if I change pair I strategy to Si star. So that is, no matter what the others are doing, I can just change this, right? So it's just the same thing as before, but now each player has such an Si star. Okay, and so I'll refer to the strategies by the other players as S minus I. And since I'm in a prime right now, I'll refer to them as S minus I prime. And so I'll just write this conveniently as Ui of Si prime and S minus I prime. It's just convenient notation because then I can just change this value without changing everything else. I'll just keep this the same for all. Yeah, just let's just keep it this. Does this make sense? So let me know.
I still didn't get what S minus I prime is.
Oh, it's just the strategy vector of the other players. So I don't want to keep writing S1 prime dot 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 Sn prime again and
Oh,
again.
yeah.
So it's just convenient notation.
Yeah, okay.
Yeah, okay. So for example, if n is 5 and if I have S1, I have S equal to S1 up to S5, then S3 is the strategy of the third player and S minus 3 is the other four strategies.
Oh, okay.
Yeah, just the strategies of the others. Okay. And so why dominant strategy equilibrium is nice is that is that it you don't really need to think about what others are doing, right? No matter what anyone else is doing, it's always better for you to just go with Si prime, right? So it's awesome in the sense. So I should
SI
highlight.
prime or SI star?
Oh, star. Sorry. Yeah, Si star. So no matter what others are doing, each player has a best strategy. Strat. Yeah. Okay. Great. And so we saw that in the first example, we have such a dominant strategy. And in fact, in the second example, we immediately saw that we don't have such a dominant strategy because we can, in fact, show that uh, isn't the best. But in the second example, we didn't actually see a dominant strategy. So, so let me just go through that once. So, so note that if okay, so let's talk about the second problem, right? Tragedy of the commons. Suppose let's take n equal to 3. Yeah. And suppose x1 and x2 are both 0. What is the best thing for x3 to do? It's best for x3 to pick half, right? Because 1 minus s over 2, we derive that formula. But if x1 equal to x2 equal to 0.4, then it's the best for x3 to do 0.1. And in fact, this is the unique best in this case, and this is the unique best in this case. And so this immediately means that we don't have such a dominant strategy here, right? There is no single value which is always the best. So immediately we know that. So immediately no DSE. So that's just there. So what's the next best thing we could hope for? So why is this strategy not a DSE? So what is wrong with this? Like, why does it not work? I mean, I did say that we can change something and uh, there's no benefit to xi, right? So then why is this not a DSE?
Because it's not best for person I. That person I can do better. If if the other person's pick something that
Sorry, could you say that once more?
like it doesn't maximize the profit of person I, right? So
If the others are 1 over n plus 1, then it does.
oh yeah, okay.
Right? Because 1 minus s over 2 is 1 over n plus 1.
But it has to hold for like every possibility, right? Not just 1 over n plus 1.
Yes, right. So it's not a DSE because in DSE, what we said is that this should be the best no matter what x1 the others matter what x1 x2 up to xn excluding xi, which is why I want to write x minus I no matter what x minus I is, right? But that is not true. So for a dominant strategy, equilibrium is best if DSE, then this should be best no matter what the other xi's are. But that's not true here. We're saying that 1 over n plus 1 is the best if the others are also 1 over n plus 1. And so that's not the same as DSE, right? Okay. And so what this really means is that we're defining something which is much weaker than a DSE. So this is sort of, so it's like um, it's like saying that um, um, so it's sort of like in one variable it's an equilibrium, right? So think about, if you can think of like a physical analog to it, with these values being something like potentials or something, that could make sense. But the point is that if the others are fixed, then there's no point in changing xi, right? But it's not the case that if a lot of these variables change, even then it's best for xi to come back to 1 over n plus 1. And so this is sort of like, it's like an equilibrium, but it's not a dominant strategy equilibrium. It is equilibrium in some sense, in a weaker sense, right? Weaker sense that if others follow the strategy, then so should we. We as the player. So should the player. More formally, so more formally, we say that the strategy vector S1, S, which is S1 up to Xn, is a Nash equilibrium if for all players I, And for any strategy Si prime and Si, the utility obtained by changing your strategy, assuming that the other strategies remain the same, is a, is can only be worse, cannot be better. So I hope it's clear what the difference between the two is. So let me know if it's not clear. So actually, let me just copy this here. So I just want you to just look at the definitions and see if it's clear to you what the difference between the two is. So also notice the what do you call these sort of variables, right? So notice that there's a for all other strategies here, but here there's a for all for only each particular SI. So the difference is that in the dominant strategy equilibrium, I can change the strategy vector for every player, while in a Nash equilibrium, I'm only changing the strategy of the player I'm considering, right? And so that is, it is not beneficial for a player to change their own strategy, assuming everything else is fixed. But in a dominant strategy equilibrium, it is not beneficial to change the strategy no matter what everyone else does. And so it directly means that a dominant strategy equilibrium is also a Nash equilibrium. And so we have this Nash equilibrium for this second case, right? So this 1 over n plus 1 all is a Nash equilibrium. Uh, can you tell me, can you find all Nash equilibria for problem 2? So tragedy of the commons, find all Nash equilibria.
This is the only one, right?
Um, I don't think so because what about this? Let's actually fix n to be 3. Yeah. What about this strategy? Is this a Nash equilibrium? Each xi to be 1.
Yes.
It is a Nash equilibrium, right? Oh, sorry. Okay, why is this stuck? Yeah, weird. Okay, so we said that 1 by 6, 1 by. We already proved that this is a Nash equilibrium.
X comma y comma z is a Nash equilibrium if x plus y comma y plus z comma z plus x is at least 1.
Good. Yes. Yes, that is right. Uh, yes, that is true. If x plus y is at least 1, y plus z is at least 1, and z plus x is at least 1. Do you see why? Because this guarantees that no matter how you change your own strategy, nobody gets anything because the sum is at least 1, no matter what you do. What about something else? So by the way, this already means that Nash equilibria is unique. In fact, NE is not unique. Okay.
Can you show the definition again?
Oh yes, sure. So it is not beneficial for you to change your own strategy, assuming that the other strategies remain fixed. That's what it means.
Right. So Nash equilibrium is not defined with respect to I, like it holds for all I.
Correct. Yes. The strategy itself has to be a Nash equilibrium. That is, for each player, it should not be beneficial for them to change from that strategy. Can you show that there are no other Nash equilibria? What's the other case? Like, if I've covered everything of this sort here, and this is Nash equilibrium sort of trivially, then what are the other cases left to be considered?
The ones with non-zero value at the end, and those you can just xi equals 1 minus s over 2 for all I, and you can solve that it has to be 1 over n plus 1.
Exactly. Yeah. And so other strategies involve, let's say I have this sort of a strategy and I'm saying that this is a Nash equilibrium. Suppose this is a Nash equilibrium and it is not of the second form. Yeah. So this is the second form and it's not of the second form. And let's say, without loss of generality or something of that sort, let's say that this is true. Then what is the best? Then what must Z be necessarily? If it's a Nash equilibrium, there's only one possibility of Z. Yes, it's just this. This is the only possibility, right? And now
Why should it be a Nash equilibrium from here?
I'm assuming this is a Nash equilibrium, right?
Yeah, so this was hold for y and x also, right?
No, but we don't know this for the others, right? We only know that one of these is less than one. So we know an or, right?
I see.
Less than one. I'm assuming that this is the case for now.
I see.
And so Z must be this. And so now what can we say about other relations? What is x plus z? It's 1 plus x minus y over 2, right? And x plus, sorry, y plus z is 1 plus y minus x over 2. And so what can we say about these being more than 1 or less than 1? Is it clear that they're both less than 1? Because this is less than 1 plus x over, well, yeah, this is less than 1 plus x plus y over 2, which is less than 1 because of this. And so since x plus z and y plus z are also less than 1, it must mean that the corresponding other variables, that is, so since this is less than 1, this means y must be 1 minus x plus z over 2. And this must mean that x is 1 minus y plus z over 2. And we already have this. And so we can just solve these and get 1 over 6 each.
Can you again take that to the computer?
Yes.
SI,
So
the definition of Nash equilibrium, S minus I is denoting S1 so on up to Si minus 1, comma, Si plus 1 so on up to Sn, right?
yes, but SI is in that correct position basically. It's not like SI is the strategy for the first player. But yes, I mean this. I mean this whole thing represents S1 comma S2 comma up to Sn.
Okay.
Yes, just the strategy is the other
Equilibrium
players.
is only about one vector.
I'm sorry.
Nash equilibrium is only about one vector. While
Yes.
DS is about all.
DSE is also about one vector actually, but it sort of behaves individually for each of them. But this is also for this, right? S star equal to this is a DSE, right? Is that clear? So basically I'm saying, so again in Nash equilibrium, it's that changing one strategy won't help the player, while in DSE it's that changing one strategy won't help the player even if others change their strategy. So in Nash equilibrium, we're not allowing others to change their strategy. That is, this remains the same. While in DSE, we're allowing others to change their strategy and saying that even if others change their we're saying that no matter what other people's strategies are, it's the best for us to choose this SI star. Is it clear so far?
Yes.
Okay. And then let's talk about the last. There are two, in fact, there are infinitely many because this is actually a family of Nash equilibria. Like anything of this form is a Nash equilibrium, right? So, for example, 1 1 1 is a Nash equilibrium, and so is 3 4 3 4 3 4. And these are terrible Nash equilibria, by the way, because it gives a value of 0 to everyone. And so is half half half. And asymmetric also 1 1 0 is also a Nash equilibrium. Yeah. Well, that's not true. Nash equilibrium only means that um, if you fix the, so why is this a Nash equilibrium? It's a Nash equilibrium because if you fix these two values, it is not beneficial for the first value to be changed, right? So it doesn't matter what this value is, the utility will remain 0, and so it's at least as good to choose 3/4 as to choose anything else here, right? And the same is true for this and for this. Similarly for 1 1 0, no matter what I change this 1 to, my utility remains 0, right? So it's at least as good to just keep it 1, and similarly at least as good to keep this 1, similarly at least as good to keep the 0, right? And so this is also a Nash equilibrium. And so these Nash equilibria all get a utility of 0. While this is a different sort of a Nash equilibria, where we derived that if these two values are 1/6, then it's the best for this to be 1/6 as well. It's we oh, not 1/6, it was 1/4, right? Sorry. It's 1 over n plus 1. Yeah, sorry. We derived the 1 over n plus 1 thing. I mean, we proved that it's an actual equilibrium before, right? We we did exactly this. In fact, we said that if these remain the same, then is it beneficial for player I to change? And we said no, right? And so we proved that this is a Nash equilibrium. Yeah, so in some sense, this is a better Nash equilibrium than this. But okay, but I I want to focus on the rock paper scissors problem, which is the 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 game theory problem that everyone is familiar with. yet it seems to not have any equilibrium. So rock, paper, scissors. Let me just copy the table. And so now there's no Nash equilibrium here. That's just weird, right? So so because it's weird because there's a theorem by Nash, of course, that every, well, let's say 2-person game let me call it finite game with finite strategies has a Nash equilibrium.
What do you mean by finite game?
Yeah, so okay, so um think about, um let's just say that this game ends. So actually let's just delete this. Yeah, every 2-person game with finite strat has a Nash equilibrium. These strategies could correspond to games of chess as well, right? Because a strategy could be like like a strategy doesn't have to be a move, right? A strategy can be actually like a function from a configuration on a chessboard to what should be played next, right? But we need that game to end infinitely many moves, so that's why I wrote it. But let's just focus on this. Yeah, so every 2-person game with finite strategies has a Nash equilibrium, but rock paper scissors seems to violate it. So
So it's wrong, the theorem.
yeah, so maybe there's a subtlety that we're missing. So
Why are there finite strategies?
and finite set of players. Um, sorry, could you say that once more?
Why are there
But you
finite?
said it's a two-person game.
Yes, yeah. So this still remains finite set of players. Sorry, someone said why is it finite strategies? Can you find more strategy?
No.
Okay, but that's, I mean, you are trying to violate something here, right? Because clearly there is some sort of a violation. So actually, it is finite strategies and it is finite set of players. But I did not. So when I say finite strategies here, what I mean is finite pure strategies, and I'll define what that means. And by and actually, let me define what an impure strategy means. An impure strategy could be of the following form. So what player A does is chooses R or P at random with probability half. This is allowed. And so this is not a pure strategy.
Wait, what is a pure strategy?
Yes. So let me tell you, but let's focus on this strategy first, and then I'll tell you what a pure strategy is. And so, and player B chooses um, S or P at random with probability half. So now these are strategies which are actually probability distributions over these strategies, right? So I have a strategy which is to play rock. I have another strategy to play paper, another strategy to play scissors. These are called pure strategies, right? These are pure. But now I could define a probability function on these, right? So maybe I play rock with probability 1/6, paper with probability 1/6, and scissors with probability 2/3, where the sum of the probabilities must be 1. And so that's also a strategy, but it's no longer pure. It- By pure, I mean that it's not like it's a deterministic strategy. I'm sort of like flipping a coin or throwing a dice or something, right? And so that's what pure strategy and mixed strategy means. So these are called impure or mixed strategies. Mixed strategies.
Actually, probability of all things should be equal for a pure strategy, right?
Uh, Not just equal, it has to be 1 for one of them and 0 for the others. So that's what pure means, right? I'm always playing rock or always playing paper or always playing scissor. Those are pure
Okay.
strategies. Yeah. So if I say 1/3 probability of playing anything, that's mixed. It's uniform, but it's a mixed strategy. Yeah. So can you tell me in this case what is the expected payoff to player A? Like what is the average amount that player A gets? What happens if player A gets rock and player B gets scissors?
1.
Okay, yes, 1. And that happens with probability 1/4. And what if player A gets rock and player B gets paper? Then it's -1, right? So -1 times 1/4. If player A gets paper and player B gets scissors, then it's another -1. And if both get paper, then it's 0. And so the expected payoff is -1/4. Right? And what about B? What is the expected payoff of B? It's just, what would it be?
It's the same, right?
But there should be a sign change, right?
Before it will be.
Oh yeah, so it's positive 1/4.
Yes, it's positive 1/4 for this. The sum must be 0, right? Because the total amount of money between the players remains 0, if you notice the table. Okay, great. And so now we have, so before we defined strategies, we meant pure strategies everywhere else. But now we have what are called mixed strategies. So what is a mixed strategy? It's it's like a probability. So we have these probabilities P1 up to Pk, where k is the size of Si, let's say, and then we can, so for a player, so I'm talking about player I. So player I executes strategy Si with probability. So maybe I should not have indexed them like this. So what I mean to say is that it's so it's like a it's like for each s, so each Si has a probability. Okay, player I executes Si with probability some P of Si, let's say, and then the sum over all these Psis should be 1. Yeah, I hope that makes sense. The notation is weird, but what I mean is that we have these strategies for a player, and so now we can sort of just give probability to each strategy. So yeah, that's what I'm saying. Is that clear?
But for any game, how are we able to find out all the possible strategies of each player?
That's defined by the game, right? The game tells us what these fundamental strategies are, which are like the actual playable moves. Like finally, like even if we had choosing these at random, finally we're making a move which is one of RPS, right? And so pure strategies are the actual moves that we make. And so mixed strategies are probability distributions over actual moves. For example, if you've played chess, then there are 20 different possible first moves. And so I could have a probability distribution which says I play e4 with probability, like the king pawn 2 steps ahead with probability half, and the queen pawn 2 steps ahead by probability half. So this is a mixed strategy because you can't actually do it, right? But a pure strategy is like playing the king pawn 2 steps forward. So we know what pure strategies are. Yeah.
So pure strategy is something that would be followed at each trial. Like
It's something that can actually be done. Like it's a legal move in the game.
no, so the like in the game of chess, then the set of strategies for each player changes after every move, right?
Yes, so then that strategy is not just one move. So the strategy there is like a function from each configuration to the next configuration. For example, I could have some algorithm that tells me, given this configuration, what should my next move be. That is one strategy.
Okay, so it is possible that the set of strategies is dynamic in nature.
Yes. Um, well, actually, not quite. So I can encode everything in one strategy, right? So I can I so in the game of chess, my S1 could be a function from every possible configuration to the next configuration, and so that's just encoded in one strategy. For example, I could have an S1. This S1 itself tells me what to do in on each step. It's all encoded in S1. So if you want to take it that way, then sure, let's just say that it's dynamic. It doesn't really matter. But basically, basically, a pure strategy is something that is not reliable on chance, while mixed strategies are probability distribution over deterministic strategies. For example, if you have one engine that always gives you the same move for a given configuration, then that is one pure strategy. But if you do something like you have two different chess engines, and now you play, and then you pick one of the engines at random at every move, and then execute that move with probability half, like whichever you picked. Like you pick one with probability half and execute the move that they suggest, then that's a mixed strategy because it's not deterministic, right? Your move may change depending on what they've suggested. So pure strategies are deterministic strategies. So I should not have said exactly that they are the ones that can actually be done. So it doesn't exactly correspond to the move, but pure strategies, pure basically means deterministic. There is no randomness involved. It's always the same. Mixed is a probability distribution over pure strategy.
So for like every game, always pure strategies would be more helpful, right? Instead of mixed.
Why is that so? Like we know here that it's not true, right? Because like why would you always go for rock or always go for paper? Or I mean, your strategy could also be this: play RPS, 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 RPS. If you're playing this over and over, that's also an allowed strategy. But that's still pure, right? Because it's deterministic, right? I'm allowed to do something like this. Let's say I play this rock paper scissors multiple times. Then this is also a pure strategy. Do RPS, 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 etc. But it's not like it's better than any other mixed strategy, because In fact, for any pure strategy, there always exists a pure strategy for the second player, such that the second player always defeats you, right? And so, of course, the second player doesn't exactly know what you're doing, but just theoretically speaking, this is always this always makes you lose, right? And so, pure strategies do not seem to always be better because of such issues. Is that clear?
But
Yeah. Okay.
why?
So,
I'm still not understanding why would someone play mixed strategies?
uh, because of the randomness, it makes because randomness itself. So if somehow the first thing was random, it was based on a coin flip, then what would you exactly do, right? Then so basically, okay. So what I'm saying is that for any pure strategy, for player A, let's call this S1. There exists a pure strategy S2 for B such that utility of S1, S2 is bad in this case for the rock, paper, scissors game. And that's clear why it is true, right? Because whatever your since your strategy is pure, it deterministically tells you what to do on step I. And so S2 can simply be just do the thing that beats it, right? But then that doesn't make sense in a mixed strategy, because in a mixed strategy there is a probability involved. So look at this strategy, for example. Look at the following mixed strategy. So what player A does is that player A plays rock with probability 1 by 3, paper with 1 by 3, and scissors with 1 by 3. Now, no matter what player B does, the expected utility of player A will always be 0. Do you see why? So, so suppose player B's strategy was to play rock with probability P1, paper with probability P2, and scissors with probability P3 in a certain round. Yeah. So then what is the expected payoff of A? When will it win? It'll win if it gets rock and B gets scissors. So that's P3 by 3 plus paper rock P1 by 3 plus scissors paper P2 by 3. And it loses when you get something like rock and here paper, which is P2 by 3 plus P3 by 3 plus P1 by 3. And note that this is 0, right? Because the probability is at to 1. And the expected payoff of B is also 0. While in a pure stat, you notice that it may happen that your opponent has a strategy that makes you lose, right? It of course it could be that you may win as well, but it's not certain why this strategy would be one that, like, for definitely not certain why the strategy is better in any way, or any pure strategy is better, right? In fact when you play rock paper scissors, it's, well, in real life you adopt weird things, but um, yeah, but the point is that this sort of a mixed strategy is sort of like fail proof, right? Because randomizing equally means that no matter what the other person does, you have an expected payoff of 0, as we showed, right? So now this extends to noting that the strategy where A plays RPS with probability 1 by 3 each, and even B plays RPS with probability 1 by 3 each, is actually a Nash equilibrium. This is a Nash equilibrium. So what I mean by Nash equilibrium here is that it's not like if B is allowed to change these values, then B benefits. B doesn't benefit from this, right? While similarly, if these values for B are the same, then A doesn't benefit by changing this. And so this is a Nash equilibrium. Is this clear?
Can you show that theorem again? The one that you
Yes.
showed 2 players.
This, yes. So
Shouldn't it be impure, or like you
So
were
it should
pure?
be finitely many pure strategies, because the number of impure strategies are infinitely many, right? Because I can assign any probability. So
All right.
yeah, the number of pure strategies is finite and the number of players is finite. Then there is a Nash equilibrium, but this equilibrium may be mixed. So possibly mixed. So please ask questions here.
Wait, what does possibly mixed mean?
That is, this Nash equilibrium may be mixed.
Wait,
So
how will an equilibrium be mixed?
for example, this is a Nash equilibrium which is mixed, right? Because uh, by mixed I mean that this strategy is mixed, right? So
Oh, okay.
yeah,
So
it's
it basically does not have to be a pure strategy.
yes, like in this example we saw this 1/4 1/4 1/4, which is a pure Nash equilibrium, right? It was not like I chose my x1 to be something random between 0 and 1. It was not the case here, but here we need that to happen. That is, we need that. So this is in fact the only Nash equilibrium. That
Wait, but how if it's like? But here it's 1 by 3 throughout. It's all equivalent.
correct, but note that this itself is a strategy, right? This is a strategy. Like this is one strategy. The strategy itself is to pick R with probability 1 by 3, P with probability 1 by 3, and
So
S with
it's
probability 1
pure.
by 3. But it's not pure because I have probabilities involved, right?
Okay, yeah.
So it's not like so a pure so even in a mixed strategy, ultimately after flipping the coin you will play something which is one of RPS, but it's called mixed strategy because you're flipping a coin.
Yeah.
Yeah, okay. So basically it is a Nash equilibrium for both players to actually pick one of RPS uniformly at random. So it's not like playing patterns like RPS, RPS, RPS or something is a Nash equilibrium. It's certainly not, right? Because like if you play something like that, then certainly there is some strategy for the other player which just dominates you, right? Every time you play R, the other player plays P. Like the player may not know that, but the point is that there exists such a strategy. Right? But here with this 1 by 3 each, we know that if A sticks to the strategy, it is in the best interest of B to stick to the strategy and vice versa.
Okay, so do we include like mixed strategies in our initial set for each I, like SI, capital SI?
No, we don't, because then this would be weird, right? Yeah. So our
Okay.
capital SIs are just the pure strategies, and a mixed strategy is a probability distribution over those strategies. And so
Okay.
for this theorem to hold true, we need those capital SI sets to be finite. Okay, great. Okay, so we've discussed Nash equilibrium. But we do want to see why the theorem is true, right? So every 2%.
Sorry, but then what is the exact statement of Nash's theorem?
Yeah, I'm writing that exactly. Yeah. So the theorem is that for okay, any game with a finite set of players, each having finitely many. When I say finitely many strategies, I mean pure strategies, but let me write that here. Each having finitely many pure strategies has a Nash equilibrium. And this was proved by Nash in 1951, I think. Very old. Okay. And okay, so let's think about two players, right? So let's try to prove it for two players first. Why would this be true? Okay, before that, I just want you to try to find the Nash equilibrium in a very small example. So it's just fun to do it. So I have, okay. So it's called the uh, who should overtake whom or something. It's, I don't remember the name of the game that it was given in the book. It had a fun name, but okay. So we have two cars, A and B, and it's sort of going perpendicular to each other. And so if they so they drive up to an intersection at the same time, and if they both cross, then they crash, which is bad, right? So if they both cross, then they get a utility of minus 100 each. But then if one of them doesn't cross, that is, yeah, one of them stops and the other crosses, then the one who crosses gets a utility of 1. The one who doesn't cross gets a utility of 0. And if none of them cross, then both have utility of 0. Right? Can you tell me the Nash equilibria here? There might be multiple.
So either both should stop or both should cross for Nash equilibrium, right?
Um, if both stop, then isn't it better for A to change their strategy to cross?
Oh yeah.
Right? You can change it and be better locally. Is this a Nash equilibrium?
Yes.
Why?
Because if the other guy you know is going to cross, you would obviously never cross. And if the other guy is going to stop, you will obviously cross.
But what if one of the guys chooses to randomize their strategy? Now you need to think about that too, right? So what if I change my strategy to stopping half the time and crossing half with half probability? We need to start thinking about those two. So let's just solve it in general, right? Suppose I have a Nash equilibrium where A crosses with probability P1 and doesn't cross with probability Q1, which is 1 minus P1, and B crosses with probability P2 and doesn't cross with probability Q2. Then what is the utility obtained by A? Utility equals, what is the probability of crash? That is, what is the probability of getting
Isn't
this minus
always
100?
optimal to either like always cross or always stop if the other guy's strategy is fixed?
If the other guy's strategy is determinist pure, then yes, because then you can sort of prove it by pigeonhole principle, right? I mean, uh, as in, if the other strategies are deterministic and your strategy is randomized, then you should just pick the one which maximizes the utility, because it's like an average over um, strategy. Like that. I hope that makes sense, right?
Yeah.
But if everything is mixed, then that may not be true. Yeah. So it could be that both strategies are mixed, in which case it may not be true that it's best to be deterministic. In fact, we'll see here that such a case will arise. So what is the utility of A here? Can someone just tell me what the utility is for this strategy?
P1 times 1 minus 101 P2.
Could you say that once more? Sorry. P1 times
1 minus 101 P2.
Hey, Shaurya, maybe try to wrap up.
yeah, I'll wrap up in some time. In which case, I think, yeah, okay, I'll wrap up in some time. And yeah, it's, why is it P1 times? Oh, did you just work it out? Uh, is it this 101
Yes.
P2? Okay, great,
Yes.
great. So he simplified the whole thing. Great. And what is B's utility? It's just symmetric, right? So it's P2 times 1 minus 101 P1. You can work it out. Basically it's minus 100 times P1 P2 plus P1 times P2. That's it, right? Wait.
P1 times
Q2.
1 minus P2.
Q2. Yes. And so this is equal to this. Right? Yeah. Good. So now, when is this a Nash equilibrium? It is a Nash equilibrium when this is greater than or equal to P1 prime times 1 minus 101 P2 for all P1 prime. And this should also be greater than or equal to P2 prime times 1 minus 101 P1 for all P2 prime.
So it's like P1 and P2 are not like 0 or 1, then they have to be 1 by. Then the other has to be 1 by 1, 0.
Exactly. So suppose P1, so suppose P2 is equal to, okay, so suppose P1 is 1, then notice that this quantity is minus 100 times P2, and so it's best for P2 to be 0, right? So if P1 is 1, then it's best for P2 to be 0, and in fact this turns out to be one Nash equilibrium. Similarly, if P1 is 0 it turns out that P2 equal to 1 is the best, etc. And so the only cases remaining is when neither P1 nor P2 is 0 or 1, in which case notice that if P2 is not equal to 1 of, okay, so if this quantity is not 0, that is if this is some non-zero quantity, then note that taking P1 to be either 0 or 1 is the best, because this is a linear function. So it'll be maximum at one of the extreme points. But then I've already eliminated that case. And so the only case that remains is when P2 and P1 are both such that this term is 0, in which case we get P1 equal to P2 equal to 1 over 101. And it's easy to see that this equality is true inequality, because changing P1 keeps utility 0. And so I have this weird Nash equilibrium as well, to cross with probability 1 over 101 and to stay with probability 0, with probability 100 over 101. Right. Okay. And what are the utilities, total utilities in both cases?
Total utilities for A or B?
Let's say I'm talking about the sum now. What about this? For this equilibrium, the sum is 0. For this equilibrium, the sum is 1, and for this also the sum is 1. So in some sense, this is better for the overall utility of all players, right? But all these three are Nash equilibria. And so one problem that often arises, I think maybe, okay, so what I'll do is that I'll try to give a sketch of the proof of this in like a handout or something, and then talk about something more on this. Yeah. But tomorrow's class is a little different from this. Maybe if we have time next week or something, then we could do something on this, but that's fine. But yeah, but the point is that remember that in dominant strategy equilibrium, whenever we have such an equilibrium, we know that it's in the best interest of players to do this. But when we have only Nash equilibrium and no dominant strategy equilibrium, it's not clear what the players should do, right? So like it's not like the players can always agree in advance what to do. And even if they could, it's not clear which strategy to follow, because for example, notice that this strategy gives utility of 1 to A and 0 to B, while this strategy gives a utility of 0 to A and 1 to B, while this strategy just gives a expected utility of 0 to both, right? And so it's not clear which of these to follow. So then there's this, so the point is that, okay, so the motivation for most of these problems is that it comes from more economic settings. For example, am I sharing my screen now?
No.
No.
Okay, that's fine. So in most so let me just give an example of an economic setting. So I think I talked about this before in a different lecture, but we have this setting called auctions. So have you seen an auction in a movie before?
Yeah.
Yeah, so you have. So people keep bidding, etc., until someone bids, and then no one else overbids that. But there are other settings in which these sort of auctions don't take place. So there are other sorts of auctions where, for example, um, for example, so basically auctions are sort of rules made by the seller for the buyer, right? And so what the seller wants to do is to devise such a rule such that either there is a dominant strategy equilibrium, which is the best possibility, right? Or devise devise rules such that there is a unique Nash equilibrium. And so there is this whole theory on how we can devise rules such that there is a unique Nash equilibrium so that it's obvious as to what to do. So if we have some other class sometime, then we could talk about this further. But for now, I'll let you all go and feel free to ask me questions. So I'll post some problems on Nash equilibrium, etc., which would be cool.
So I'll end recording then.
Yeah. You can end the recording.
Awesome.